This video is going to attempt to explain the trends in atomic radius and also ionic radius. So to start with, let's identify what these terms mean. Atomic radius is effectively the distance from the nucleus of an atom to its outer electrons. Although this is a little bit difficult to measure because according to the atomic orbital model, there's no real defined edge of the atom. So in reality, the way we actually calculate the distance from the nucleus to the outer electrons is by measuring the distance between two neighbouring nuclei of atoms that might be bonded together, and then halving that distance to find the atomic radius. You can find the IB values for atomic radius in the data booklet. Ionic radius is a very similar principle, except this time we're considering the radius of an ion and not an atom. And it's worth remembering that an ion is simply an atom that has lost or gained electrons, so will always have either a positive or a negative charge. Let's first then consider the trends in atomic and ionic radiuses down a group. In this example, we'll look at the group 1 elements, lithium, sodium and potassium, but know that the same trend is true of the other groups in the periodic table, with the exception of the D block elements, who require their own explanation. There is a Bohr model for lithium, sodium, potassium, and if I find the values for atomic radius in the data booklet, they look something like this. As you can see, the atomic radius increases as I go down a group, and the reason for that is that my outer electrons are in progressively higher energy levels that are further from the nucleus. Let's now have a look at the ionic radii for these elements. And you'll notice that for each of these elements, when they form an ion, they become positively charged because group 1 elements lose one electron in order to complete the octet rule. And just like the atomic radius trend, we see that the ionic radiuses increase down a group because, again, the outer electrons are in a higher energy level further from the nucleus as I move down the group. It's also useful to compare the atomic radius for each atom with the radius of its ion. And you'll see that in each case the atomic radius is larger than the ionic radius. To explain this, we need to recognise that each of those group 1 elements is losing one electron, meaning that the number of occupied energy levels is decreasing. So when forming a positive ion, that positive ion is always going to have a smaller radius than its parent atom. Let's now consider the trend across a period. Let's use the period 3 elements as an example here. And I'll write down the atomic radii from the data booklet. And you can see a clear trend here from left to right that the atomic radius is decreasing. And this is because the outer electrons for elements in the same period are all in the same energy level, so they receive the same shielding from the nucleus. However, the number of protons in the nucleus, or the nuclear charge, is increasing by 1 as I move across. So that increased number of protons in the nucleus means a greater electrostatic attraction to the outer electrons, pulling them closer. Let's now add the ionic radii for these elements. In this case, there's no clear trend going from left to right, so we need to consider the positive ions and negative ions separately. Let's first consider how the radius of the positive ions compares to their parent atoms. You can see here that in each case the radius of the ion is smaller than the radius of the parent atom. And as we discussed with the group 1 metals, this is because in each case the atoms are losing their valence electrons, therefore losing a valence energy level. For example, when a sodium atom loses its electron, the sodium ion is left with only 2 occupied energy levels, instead of the 3 that it started with. Therefore the radius decreases. What then about the formation of negative ions from an atom? Well, in this case I can see that negative ions always seem to have much greater radii compared to their parent atoms. To explain this, we need to consider that adding another electron to the valence energy level is going to increase the amount of repulsion between the electrons in that energy level. And this has the effect of causing the energy level to expand. Therefore, the ionic radius will always increase for a negative ion. Here's an example using chlorine, for example. Of course, the more electrons I add to that valence energy level, the more repulsion there will be between the electrons, and the larger the ionic radius will become. Let's now summarise the key factors to consider in questions about atomic and ionic radius. Firstly, for questions related to the size of atoms, we need to consider the position of valence electrons, i.e. which energy level are they in, and we also need to consider the nuclear charge, or the number of protons in the nucleus of that atom. When comparing the size of ions, or the ionic radius, to that of the parent atom, we first need to consider if the atom has lost or gained electrons. For atoms that lose electrons and become positive ions, the ionic radius will be smaller than the atomic radius because a valence energy level has been lost. And for atoms that gain electrons and become negative ions, the extra repulsion between electrons in the valence energy level will cause ions to become larger than the parent atoms. And that's about it for atomic and ionic radii. Hopefully this video is of some help.